I'm really excited today to talk to you about distributed training and especially how some of the new features we have announced with Snowflake ML makes it very easy to do distributed training in Snowflake now. So standard disclaimer slide. We will talk about some of the features that are coming soon, so we are required to put up this slide. So let me introduce myself. My name is Jeffrey. I work on the ML team at Snowflake. Been with Snowflake for about 2 years now. I lead a bunch of initiatives that make up Snowflake ML. So in terms of agenda for today, so we'll talk a bit about the challenges in scaling ML model training. We will see how some of the new features in Snowflake ML have made it really easy now to do distributed training. We will deep dive on the user experience, in particular the new APIs that we now have in Snowflake ML. And finally, we will see a live demo of training a PyTorch model, all on Snowflake data, all within Snowflake. So let me give you a sneak preview of the talk. So what you see scrolling on the right side is a model definition and model training code for a fairly capable recommendation model. You don't have to squint too hard. We will look at it in detail. But by the end of this talk, we're going to take a model like that, and we're going to train that model on your Snowflake data with just a few lines of extra code. And all of that runs on fully managed and serverless infrastructure. So the key point I want you all to take away is distributed training has become really simple to do in Snowflake now. And if you're considering doing distributed training, there is no easy way to do it than with these new APIs that we have now launched. So to get started, just recapping the Snowflake ML stack. So Snowflake ML now is a very comprehensive and integrated set of capabilities that allow you to do end-to-end ML all within Snowflake. We have Snowflake notebooks, where we expect that to be the entry point for most of you for these workflows. And then we have a number of libraries that cover the entire ML lifecycle, and then all of it is powered with, we have the new container runtime in addition to the existing warehouse runtime. Simple question, why or when do you need distributed training? And the simple answer is when you want to speed up your model training, right? And a lot of times it has to do with your data size is growing, your data sets are bigger, what was taking a few minutes before is taking a few hours, and you want to speed it up. And subsequently, what that means is if you're able to speed up your training, you can run more experiments, you can iterate faster, and you can get to insights faster, right? So the simple answer is you just want to speed up, and you want to throw more machines at the problem and scale out, right? So in terms of use cases for distributed training, fairly broad. These are some of the use cases we hear quite frequently from our customers. They're not specific to structured or unstructured data. They're not specific to traditional ML or deep learning. Whether you're doing XGBoost, whether you're doing PyTorch, you can speed up your workflows with distributed training. And today we'll see an example of a recommendation model, but we see fairly common use cases in fraud detection, lifetime value prediction, or very classic unstructured use cases in computer vision or NLP. When it comes to how do you distribute the training, the concepts are fairly simple. There are two common ways to do it. One is called data parallel training, and the other is called model parallel training. There are a few other more exotic types, but for the purpose of this talk, we'll just stick to these two. The idea with data parallel training is very simple. You have a large data set. You want to process it with multiple machines. So you're going to partition your data, and each worker gets a different partition, and each worker trains on that partition of the data, and then finally they all collaborate to get to one good final model. And the idea with model parallelism is when your model is really large and memory intensive, that it really does not fit on one box. The model itself gets split into different model partitions, and each node gets the same copy of the data, and then they all collaborate to one single model, right? So those are the two common ways. We will look at an example of data parallelism later in the demo today. So let's talk a bit about challenges in scaling, right? And the main takeaway I want all of you to have here is a lot of the model training happens with open source libraries, right? But there is still a lot of work in making it work within your environment of choice, in this case, Snowflake, right? So we have distilled it into these 4 themes. So the first one, especially in Snowflake, is with data management, right? Most of your data in Snowflake is in Snowflake tables, and that you're running a lot of your analytical workloads on that. But then when you want to do large scale, scale out training, you always think about, is that the right format? Do I need to move it to a different cluster? How does that work? Do I need to build a pipeline? And if you are building a pipeline, you need to then manage it, monitor it, and that's a whole bunch of work. Orchestration is another one. A lot of the orchestration these days come out of the box with modern frameworks and libraries, so that is great. But there is still a lot of work to run. If you get into running this on a schedule, let's say daily or weekly or something, there is still a lot of work to make sure that these things run reliably. The third one that I particularly have experienced a lot is with environment consistency, right? Most of you might have seen, your teams have one environment for where they do their experiments, and then there might be another environment where you're doing your production. And a lot of times, subtle differences in these environments lead to a lot of challenges for the team. And you'll often see your teams spinning at their wheels, figuring out why did this Python version not work in this other case, and so on, right? And finally, you don't want to get bottlenecked by choice of instances, so you want to make sure that you have access to a broad range of capable CPU and GPU machines to scale up this training. We'll drill into some of this a bit more, right? So I talked about data management. A lot of times it has to also do with data formats, right? So when you are moving your data for distributed training or large-scale model training, there's a question of what is the right format, right? And am I now converting from one representation to the other representation? Am I doing it the right way? Is it the most efficient way? And if I'm doing it, how often should I do it, and so on? Data distribution is the other one. We talked about data parallel, right? So how are you going to split your data in a way that your training can work well? Should you split it into 1 MB files, or should you split it into 1 GB files, right? And how do you make sure that they're shuffled correctly? Because a lot of times for training, it matters the order of records in your data. There's a lot of work in figuring that out. Then finally, as you do these processes, you're also generating a lot of new data assets, right? New data. You'll have one copy of data, then the next copy of data, and some of them might be features, some of them might be checkpoints, and how do you reason through them very quickly? So for instance, if you realize that maybe a feature that came last week was bogus, you want to quickly figure out which models are impacted, right? And there's a lot of extra work for you a lot of bookkeeping for you to do to answer that question very fast. And then finally, how do you do all of this without breaking your governance and security? And you don't want to compromise any of that. When it comes to orchestration, doing a single run is easy, but when you're running it on a schedule at scale, these things fail, especially if you're running it on powerful instance types like GPUs. You will see that they fail once in a while, right? How do you make sure you're not losing all your progress when one of these events happen, right? There's also a lot of work in experimenting with different types of backends and figuring out what is the right backend depending on the type of training you're doing. Does it change when you go from a single node multi-GPU to multiple nodes and so on? And then resource utilization. You are running these processes on very expensive instance types. So there's always this worry, are you getting the right utilization from these instances, right? And the third is with environment consistency. The common thing we hear is how do I kind of take my notebook, or how do I productionize my script, or how do I give my notebook to my ML engineer, and how do they make it successful? There's a lot of work in that handoff process because often those are different teams or different personas, and you can end up with some challenges there. And a lot of it has to do with package version inconsistencies, environment inconsistencies, and so on. And finally, reproducibility. Unless you have all of those environment consistencies, you really can't get the reproducibility for your training runs, right? So now, I've talked about the challenges that you might often run into, and you'll see all of these challenges have nothing to do with the model or the type of model or the type of features. It's preventing you from iterating on your true value prop, right? So let's see how some of the new features in Snowflake ML starts to address some of these problems. So container runtimes are a new managed container offering, new managed layer on top of our container services platform, Snowpark Container Services. So there is no need for you now to build your containers. We provide prepackaged environments, and we have done the hard work of making sure that these have the latest and greatest libraries from all the popular frameworks. And we take care of the vulnerability scanning and so on. So you get a really good base set to work with. We make it available on both CPU and GPU, so that way you can run a training on GPU as well. And the third one is what I'm really excited about, because what we have done is we want to take away all the undifferentiated stuff, right? So we have baked in a lot of optimizations right into the runtime. So a common question we hear is, great, I have my container platform. How do I bring in my Snowflake data? How do I bring it in an efficient manner? We have done the hard work of doing that for you. So with just a few lines of code, you can now bring it in without worrying about all the challenges we talked about before. And we've also made scaling out very simple. So imagine you start with 1 node and you want to go to 4 nodes. It's just a single line of code change now. We'll see that in the demo. And finally, it is very highly integrated with the rest of Snowflake, so you don't have to do the hard work of figuring out how do I make it work with model registry or with Snowpark and so on, right? Container runtimes are now available to use with notebooks. That is the first offering we have with container runtime. And it's really easy to get started. You can go to Snowside, you can start a notebook. Instead of choosing the standard runtime, you can choose a container runtime. And you'll get a drop-down where you can choose the CPU or GPU version of the runtime. And at the bottom, you can see the compute pool. So if your admin has set up a few compute pools, you can run this on any of those compute pools now. And that's it. That's all required to get started. And container runtimes start to address some of the environment inconsistency issues we talked about, because by scheduling notebooks, you can now run these in production with the same bits. And how do you address some of the data management challenges we talked about? How do you address some of the scale-out challenges we talked about? So we have now added more features to our existing Snowpark ML modeling so that you can now run these scale-out training workflows also on the container runtime in addition to the warehouse runtime. So just for folks who have not seen Snowpark ML modeling before, Snowpark ML modeling is our developer toolkit that allows you to do pre-processing and training on all the popular frameworks, XGBoost, scikit-learn, and so on. And we have now added PyTorch in there. We have a new interface for PyTorch. And in addition to that, what we have done is we have actually updated these libraries such that they can run on both the existing warehouse runtime as well as the new container runtime. And these come pre-installed on all Snowflake notebooks, so there is no extra installation to get started. So with that said, let's dive a bit into the Python API. So as I said, when we thought about how to design an API for distributed training, the tenet we wanted to follow was as minimal changes to your code as possible, right? We don't want you to have to change your code a lot just to make it work within Snowflake. So we thought about what are the things that, as a developer, you would think about, okay, I know the model I want to train in Snowflake, but what are the things you would think about to make it work within Snowflake, right? So the first is data loading. How are you going to bring data that is in a Snowflake table to your training process? And how do you do that in an easy manner and don't have to spin your wheels thinking about performance, governance, and so on? The other thing is with scale out, right? Even though a lot of the open source libraries give you the nice primitives to do distributed training, how do you actually make it work within Snowflake? How do you figure out all the communication? How do you figure out all the scaling? We have made that completely abstracted for you. It's just one line right now. And finally, it's all tightly integrated with Snowflake, right? And what I mean by that is we just want you to do your work, and we will make sure that we are tracking lineage, we are tracking your models in registry, and so on, right? So there is no extra overhead for you to, okay, I know my script, I have to now spend weeks making it work within Snowflake. That is no longer there, right? For data loading, we have now introduced a new concept called Snowflake datasets. So what is Snowflake datasets? So when you're doing training, you often want an immutable copy of your data. You don't because reproducibility is very important in your training workflows. So we introduced Snowflake datasets, which is a new schema level object for managing your training datasets. What that means is at the time you've completed your pre-processing and you're sure that this is now your data set that you want to try out different models, you want to iterate on, you want to do hyperparameter tuning, you can now persist that, and that is a new schema level object. That means your team can now experiment on it. We support versioning on these data sets, and they're fairly flexible. And the way you generate a data set is you can either generate it from a Snowpark data frame. So once you've completed all your data transformations, you can just generate it from a Snowpark data frame. Or if you're using Snowflake Feature Store, you can generate a data set from a bunch of feature views with the Feature Store API. Some more detail about the data ingestion. So as I mentioned before, if you are using your data frame, you can continue to use your data frame for training. All our APIs work equally well, continue to work well with the data frame abstraction. And what that means is when you're doing your experimentation, there is no extra materialization of the data for training. And what we do behind the scenes is we actually read off cached query data, which means it'll be faster than you trying to do the same workflow anywhere outside. At the point you are sure that this is the data set that you want to work with, all the pre-processing steps have completed, you can persist that data set. And if you're using our APIs, we take care of the materialization at the right point. What that means is we will go now materialize those as Parquet files on an internal stage, and then those are made available to your container runtime, so you can access those and into your ML frameworks, right? And we've also made it easy to read these things as framework-specific abstractions. What I mean by that is if you're using PyTorch, if you've written PyTorch code, you start with your data, you generate your torch data pipes, and then you generate a data loader, right? We make that very simple with the dataset new abstraction. You can just generate torch data pipes or TensorFlow datasets directly from a Snowflake dataset. Right, so you can see how we have made it just really simple to go from a table to a Snowflake dataset to the abstractions in deep learning frameworks. And as you do that, as I mentioned before, we capture lineage automatically, and that is really cool because there's no extra code you need to do to track these relationships, right? Let's see a code example. So you're creating a data frame directly reading off a table. In this example, we are reading from a customer features table. We have a new method on the dataset class called create from data frame. So this is how you create a data set from a data frame. You can see you can give it a name, you can give it a version, you can give some additional metadata like labels and so on. What that does behind the scenes is it will actually go and materialize into a Snowflake data set. If you have an existing data set, you can just load that. And once you have a data set, as I said before, in this case is an example with PyTorch, you can read this directly into torch data pipes and then pass it to a data loader that gives you the standard IEEE interfaces that PyTorch recommends you use, right? And that's it. That's all the work to train on your Snowflake data, right? It can't get simpler than this. And behind the scenes, we are doing all the heavy lifting to make sure that those are all happening in the right manner so that your training processes are optimized. Let's talk about scale out now, right? So we saw how you can bring your Snowflake, your open source training code in and how you can connect that with your Snowflake data. Let's see how easy it is to scale out now because you have your script working on a single node and you want to make sure that you want to now try out larger machines and you want to scale this out, right? We have now introduced new trainer interface in Snowflake ML. So what that means is we have new wrapper classes for these frameworks. So for PyTorch, we have a PyTorch trainer now. And on the PyTorch trainer, it is very easy for you to scale out with just a single line of code. We'll see an example. And behind the scenes, Snowflake is taking care of all the distributed training orchestration. We are doing the hard work of figuring out the right processes, spinning up the right containers, figuring out all the communication, optimizing that, and so on. And this does not mean that you lose flexibility, right? Because a lot of times, you may want to experiment with a slightly different backend, right? Or you want to maybe change the way you're placing compute on different devices when you're doing distributed training. We don't take that flexibility away. We give you a pre-populated context object. So what that means is when you're running on a compute pool, we populate a context object such that the context object has enough information for you to configure your backend as needed. So we'll see a code example. So this is very standard PyTorch training code. Anyone who has looked at a PyTorch tutorial will recognize this code. So you have a model definition where you're defining your model. You define the standard forward pass, you define your loss functions, your optimizers, and there is a very standard data loop, training loop where you iterate over the data and you train, right? So this is all standard PyTorch training code. No changes, bring it in. There is no Snowflake specific code here, right? This is a model definition. Now, the standard way in PyTorch, for example, to make it distributed is you use an abstraction called DDP, which is Standard Distributed Data Parallel. PyTorch offers a variety of different abstractions for distributed training. In this example, we're using Distributed Data Parallel. And you can see the context object I talked about before. So you have a new PyTorch context object, and the context object gives you helper functions to get the rank, the world size, and so on. These are all PyTorch specific concepts, but these allow you to configure the backend as needed. Right? So, and these are set based on the cluster configuration you're running in, right? So if you're running on, let's say, a 4-node machine, then the world size becomes four times the number of devices that are there. And that's about it, right? You can get the context object, you can use the context object to populate the right parameters. And then finally, you're bringing it all together, you have a PyTorch trainer, where we pass in the train function we had before, which was all standard PyTorch code. And then you have a scaling configuration where you can set the number of nodes, the number of devices, number of workers per node, and a few other parameters, right? And that's it. Training now gets spun up for you. And now we'll see a demo. So I'm going to switch over. So the idea with this demo is not to go too deep into the model, but to explain how you can take a very capable model and how you can bring it into Snowflake and train it all within, right? So I am in a Snowflake notebook. I'm just going to go click start. You can see at the top, this is a notebook running on a container runtime. You can see the warehouse we are using. So if you're running any SQL or Snowpark operations on this notebook, they will all get pushed down to the SQL warehouse. You can see the compute pool we are using, and you can see in this case we're using a GPU runtime. This notebook is running on a compute pool with 2 nodes. So we're going to try running training on 2 nodes in this example. So this is a recommendation problem. The data set we're going to use is called the Tasty Bytes data set, which is used in a lot of our demos. The idea is very simple. Tasty Bytes is a brand of food trucks. And the idea is you have transaction data from a bunch of food trucks. And we are going to try to use that transaction data along with customer information and some features about the different menu items to predict new menu items for customers. So it's a very classic recommendation problem. So what I'm going to do is I'm just going to run all the cells in this notebook, and then we can talk through as they run. So the first thing I do is I get a Snowpark session that is very easy to do in a notebook. And with a SQL cell, I'm able to just look at my table. So in this case, I'm just describing the customer table. You can see a bunch of standard customer demographic type information over there. And note that I'm mixing Python and SQL cells in this notebook very easily, so that's cool. And just some basic statistics about the data. There's some 200,000 records, about 1 million purchase records, and so on. Now, because I want to visualize some parts of my data, I'm going to install a bunch of standard visualization libraries into the notebook. And this is an idea, right? So on the vertical axis, you have all the customers, and then on the horizontal axis, you have all the menu items. The white pixels mean someone bought a menu item there, and the darker they are, that means people have not bought them. So you can see it's very sparse, very classic recommendation example, and you want to see which one of those dark spots can you recommend to the customer. In this example, I'm using a standard pivot table functionality from Snowpark to do it. So that's all good. I'm using Snowpark to join all the 3 tables I have. One contains the customer information, one contains the menu information, one contains the purchase transaction information. So you can see this is the shape of the data set. You can see it's keyed on customer IDs, and you have a bunch of information bringing it all together. So the idea with the recommendation model is you treat your categorical features and you treat your numeric features slightly differently. Categorical features tend to be very sparse, so you want to treat them slightly differently than you treat your dense features. So we are just listing all of them out. And because our model just understands numeric data, we are going to use some of Snowpark ML's functionality to convert all the categoricals into numerics. Here we are using Snowpark ML's label encoder and min-max scaler. The label encoder will encode the categorical values to numeric values, and then the scaler will scale numeric values into a 0-1 range. And after you do that, this is what it looks like. So previously you had all these categorical values, country is Germany and so on, and now you are encoding it into a number. So now it's starting to get into a shape that the model can work with. Out of curiosity, I also wanted to just see if there are any interesting correlations in this data set. So I'm using Snowpark ML's distributed correlation function to just see a bunch of correlations and see if there is anything interesting. I'm using Seaborn to look at this. I didn't find much interesting other than confirming that there is no feature target leak or anything funky like that. Okay, so those are all standard data transformations you've done. You've done some encoding and so on. And what we're going to do is we're going to take that pre-processed data frame. So hopefully the idea you're getting is you can do all of your feature transformations with standard Snowpark. You can push down to the warehouse. You can take advantage of all the scale-out functionality. And now how are you going to use that pre-processed data for distributed training, right? So the model we're using is called Deep Learning Recommendation Model, DLRM. It is an open source model. You can find it on GitHub. There are a bunch of PyTorch implementations available. The idea is very simple. As I mentioned before, you have your categorical features that you pass through an embedding bag, and then you have your numerical features, and there is a feature interaction layer which will capture the feature pairwise interactions of all your features, and then finally there are a few standard MLP layers. We're not going to go too detail into the model, other than the only thing you want to take away is this is a very capable model. This is a model that is used in the MLPerf benchmark, for example, for recommendation. So the model definition for this kind of a model is in this cell. This cell there is no Snowflake specific code in the cell. You can see we are defining the feature interaction layer, we're defining the forward pass. For the DLRM model, we're defining the embedding layer, the feature layer, the two MLP layers. All of this code is what anyone would run on your laptop if you're using PyTorch, right? There is nothing Snowflake specific about it. So we have defined the necessary classes to define this model. And what we're going to do is, because I want to complete training within this demo, I'm just going to sample 100K rows. So on the data frame, I'm just going to sample 100K rows and then split it 80, 10, 10. 80 for training, 10 for testing, and 10 for validation. And now I have 3 data frames: train data, val data, and test data. And from here, I want to start creating my data sets. So you can see I'm using the new helper functions to create a new data set. I'm giving it a name. The version is v21. That's how many times I've run this demo. And if I didn't want to create a data frame, I could have also loaded a data set from before. So here comes the fun part. So this is where we write the training loop, right? And as I mentioned before, you can see the imports at the top. They're all Torch specific. They're all specific to PyTorch. The thing I want to do is I want to configure my distributed training. So as I mentioned before, I'm using the context object. And from the context object, I'm getting the necessary rank and the world size, which I'm able to use to then set up the process group. So in this case, I'm using what is called a glue backend. You can also use a nickel backend. In this example, we're using glue, and then from the context object, I'm setting the rank and the world size, right? So this code remains the same even if you were going to run this on a 10-node machine, right? Because what you get in that context object is dynamic based on your cluster configuration, right? So this code all remains the same. The only additions you have made is you have you're fetching the required dynamic information, and then you're setting your backend. The context object also gives you the dataset map. So as I mentioned before, on your training and validation datasets, from the dataset, you can now generate a Torch data pipe. And when you generate the Torch data pipe, you have access over the batch size, the shuffling, and so on. And in this example, we are shuffling, and we are picking a batch size of 1,000 just so that we can complete the training within this demo. And once you have a Torch data pipe, you can then pass it to a data loader. And from there, it's all standard PyTorch again, right? So folks who have written any kind of PyTorch training before would be very familiar with this flow. And the only additions we have made are those few lines where we fetch from the context object, and then we generate the Torch data pipe from the dataset. And behind the scenes, there is a lot of heavy lifting happening, going from table to necessary files on stage, to partitioning them, shuffling them, and reading them in an iterable interface, right? So now that we have it, the remaining code is very standard. We are wrapping the model with what's called DDP, which is Distributed Data Parallel. Distributed Data Parallel is an existing PyTorch abstraction. There's nothing Snowflake specific about it. And then this is a standard training loop where you iterate over your data, and you're doing the necessary forward and backward passes, and we're printing out some information about the epochs and all that. So there's nothing Snowflake specific on this. This is all standard training loop. And at the end, we will destroy the process group as well. So I'm not going too deep into the specifics of the PyTorch training code. That is not the focus here, right? So the model definition, to recap, the model definition was whatever you write that works on your laptop. The training loop, you just configure it with the context object, and the data set you load as Torch data pipes with our helper libraries. Now, bringing it all together is with the PyTorch trainer interface. So you can see I'm passing in the train function we defined before. And the scaling configuration is what's interesting. Here I'm using num nodes as 2, which means now we are telling the trainer to run this on 2 nodes. And that's a very powerful line because behind the scenes we are spinning up the new node, we are spinning up the necessary container processes, we're figuring out the communication between them, and all of that is happening. And you also get, as I mentioned before, you don't lose your flexibility, so you can configure each worker separately if you want, but otherwise we have good defaults that you can use, and that's about it, and then you run the training. So I will scroll to the end of the training here. So it's a little chatty, the logs are a bit chatty, but these are all for data loading. But towards the end, let's see, yes, there we go. So towards the end, you can start to see some of the actual training log lines that we had in the code start to print out. So you can see in this example, the lines without that IP address is the first node, and the line with the IP address is probably the second node. So you can see for each epoch, we are running it on 2 nodes, and we are processing 1,000 records, and it's a fairly trivial run, right? But you can see these logs are now streamed right into your laptop, into your notebook. And in this case, there were just 2 epochs, so it all completed very fast. But hopefully you got the idea that if you want to do this workflow outside of Snowflake, you have to build your containers, you have to figure out the communication, you have to figure out how to bring the Snowflake data, right? We have done that hard work for you, right? And the rest of the notebook is, we are running a bunch of evaluations on the model. This model had an AUC of 0.655, which is not great, but we also just ran it for two epochs, and then we are saving the model to registry. And that's about it, right? So hopefully that made sense to you, like how easy it is to bring a very powerful model and just run the training within Snowflake. And that's about it. I think that's the end of the demo. If you want to get started, we have a bunch of examples and quick starts already, and that's about it.